Mike, and welcome back to BitFixer. This is part 2 of DG April, where we're looking at the digital group, and this time we're going to be focusing on software that was available at the time, the different types of storage devices you could use with this computer, and we'll also look at a digital group emulator and building new software for the digital group this year. So, hope you enjoy it. The first and probably most common option for the digital group was to load software from cassette. The digital group computer I have does this, and it uses a TV readout and cassette interface board, which you can see here, as well as the 256-byte ROM on the Z80 processor card. A disk drive unit was available as well. Digital Group offered a single or double 8-inch drive unit with controller. That would set you back $745 in 1977 for a single drive and interface, or $995 including the enclosure and cables and everything else, and power supply. A 5¼ inch version was also available. And there was a third storage option which I believe was unique to the digital group. It's this device called the FiDeck, which is essentially a group of independent cassette players and recorders that are all controlled by the computer at the same time with a controller card, and that was kind of a bridge between the cassette world and the disc-based world. It came in a 2-unit and a 4-unit model like the one here in this Popular Electronics ad, and yeah, that was kind of an interesting storage device that they had available. And here's another ad showing off the vast collection of software they had available. Presumably this shows audio cassette and disc-based software, as well as FiDeck-based cassette software. So far I've only been able to find a few of the audio-based pieces of software, but I'm on the lookout all the time for other things. Here's a price list of some digital group software, so you get an idea of what it cost in the late 70s for these things. It's a company called Microcom that offered a operating system called MCOS. That would be pretty interesting to check out, but I've not been able to track that down, or any other disk software for that matter. And another price list for software here. There was another operating system called Oasis that was disk-based as well, and you see a bunch of programming productivity tools, as well as, yeah, we have an assembler here. We've got, what else? We have games, a bunch of games. So you get an idea of the variety of software that was available for a digital group at the time. So what can we actually try out today? So we have a few audio copies of cassette-based software, like we saw last time, like this Lunar Lander game, and a few other applications like a word processor. There's a couple options of BASIC, and I really started thinking about how we can preserve the software for the digital group. We have audio copies of some of the software, but in some cases the tapes are fairly degraded, so they don't load properly. But what I really wanted to do was create an option for creating some new software in the digital group, as well as preserving the existing software. We can preserve some of the audio-based software by making a digital copy of it, like you see here. I'm just going to take a look at this one, and we'll see how you actually store data in an audio recording. So basically the technique you use for storing data on an audio cassette tape is something called frequency shift keying, or specifically audio frequency shift keying, or AFSK. Generally you have two different frequencies you use. One is, there's a 0 frequency and a 1 frequency, and they both they correspond to a 1 or a 0 bit as you go along. And you've probably heard the the way one of these cassette recordings sound. So let me just play. This is the Lunar Lander program. So you have that sound there. It's sort of modem-like sound, and basically what you're hearing there is you're hearing rapid switching between those 0 and 1 frequencies. And at the beginning of the recording, you have a long period of the, in this case, it is the, I think it's the 1 frequency. Well, anyway, one of those two frequencies is leader at the beginning of the audio file. So, making the audio recording of a piece of cassette software is great, because then you're no longer subject to those tapes degrading and potentially losing data. So you're kind of frozen them in time, but we don't yet have we haven't really recovered the bytes of the software yet. So that leads me to some code that you can see here is quite old, 10 years ago. This is a repo some code I threw up on GitHub here for a digital group emulator that I worked on a long time ago. And that includes a script here, which for some reason I wrote it in PHP. I guess I was doing a lot of web development at the time. But this basically goes through, takes an audio file and converts it to, or attempts to convert it to, a raw binary file that can be run by a digital group emulator. And the way it does that is basically it goes through the entire file and tries to find all of the zero crossings. So basically that's where the audio signal is going above or below 0, and it uses that to basically find the 0 bits and the 1 bits and to demodulate them, decode them back into a raw binary file. And in the case of the digital group format for encoded audio, you have 2 frequencies which are in here somewhere. Here we go. We have a high frequency of 2975 and a low frequency of 2125, which is kind of interesting because there was actually a standard for saving binary data onto an audio cassette. There was the Kansas City standard at the time. I don't know if necessarily everybody followed it, but at least some computers may have used it, which specified 300 baud, and the two different frequencies were 2400 and 1200 hertz. But in the case of the digital group, it uses these two, 2975 and 2125. So looking at the documentation for the TV interface and cassette card here, I just wanted to figure out how those 2 cassette frequencies were derived. And it looks like here it's taking the TV master oscillator, dividing it by 2 different numbers, and then you get 2125 or 2975 hertz. So that's how they got those, and that's probably why you wouldn't adhere to another standard, because you already had the oscillator on there, so you're just going to do something that's convenient for this particular card. So that makes sense. Let's run that script on the audio version of the Lunar Lander program. There you go, it's doing its thing. And now we have generated a file called, this was ll.wave, so this is ll.bin. And we can see that we've gone through the entire wave file and we've converted it into the binary version of what was stored on the audio cassette. And interesting thing here is that the content, part of the sort of archaeology of doing this was to figure out what the header of a digital group program looked like. You can see at the beginning here, they all start with this 5353 pretty much, and this I believe is an octal address, which would indicate where the code should go. And there's a few other bytes here, and there's another address in here somewhere. I have that somewhere where we can find it, but there's a header of a few bytes here, and then the entire rest of it is Z80 opcodes. So the rest of it is all machine code, which just runs directly on the processor. So now what we can do is we can actually take that binary file, which is now we can consider that preserved. We've preserved this program, and then we can regenerate the audio file and load it back in on the real hardware. And now let's look for a moment at the digital group emulator, the DG-EMU. This is a pretty rudimentary emulator, but it does run in more or less the way that a digital group system, a Z80 digital group system with a cassette board would work. In order to support simulating loading from cassette, what I did was I took the this is the audio ROM. This header file has the contents of the audio ROM, and this section here, this is a subroutine that basically reads from the cassette board, and it does all the work necessary to figure out if the the various audio coming in is a 1 or a 0. And I just modified this ROM. I zeroed out all these this whole routine, which conveniently on a Z80 00 is a no-op, which is really nice. Makes it easy to test things. And just at the I just kept the subroutine the same length, but then at the bottom I just do I read from port 001, which on a Z80 is you're reading from an I/O port, and that's something that's simulated in the rest of the emulator. So I can specify a file that I want to load, one of those binary files, and then instead of having it attempt to load from simulated cassette or anything like that, it just loads the bytes directly. And then here's the emulator itself. Basically, it just uses there's a Z80 simulator that I've linked to, Z80EX, I believe, and it will start at just like a real Z80. It starts at address 0, and it starts pulling data off of memory, the virtual memory here, and then it will execute the instructions. And then instead of, like I said, instead of loading from a real tape, you can specify a file name, and then it will just load directly from that file. So let's go ahead and take a look at what happens when you try to run the Lunar Lander program on here. All right, let's go ahead and try out this emulator. So I'm going to build it. Okay, and then let's go ahead and run. And what comes up here, it's actually using Curse's library on Linux here to do the animation. So this prompts you for the name of the tape file, and in this case it's LL for lunarlander.bin. And it goes ahead and loads it in. You can see the timing is not exactly matching up with the digital group right now. That's something I'm working on this thing. Just attempting to time it based on the cycle count of each instruction, but it doesn't quite work yet. So we will get that improved. So hit 7 for Lunar Lander, and you can see there you go. And the reason it's flashing there is because the digital group TV card is not capable of independently accessing characters on the screen, so it actually has to clear the screen in between every update. And you can also see that something is a little bit messed up here. That's almost certainly a bug in the emulator, which I'll have to look at. But let's take a look at something. Let's take a look at a simpler program here. Here's another one, Kingdom game. Oh, somehow the backspace is still broken on this emulator. To be fixed. And there we go, running Kingdom, the famous game. Let's see, I'll buy 10 acres. I'll sell 0 acres. I don't know. How many food bushels? 20. Anyway, it works. So definitely this doesn't, that import or the conversion script is still a little bit flaky, and I'm not convinced that it converts everything without errors yet, but still working on it. But as you can see, this does have the potential for archiving or permanently archiving some of the digital group software, which I'd really like to do, and I'd really like to get some more software recovered from audio form like this. And finally, let's look at how we would actually go about building some new software for the digital group. Now, you could run one of the basic interpreters and write some basic programs, but I wanted to see if I could get a compiled C program to completely run on an original on the original digital group hardware. So looking around, I did find a compiler that supported compiling to Z80 object code, and it's called SDCC, or Small Device C Compiler. And I've gone ahead and put together a sort of template C program here that actually calls some of the routines in the ROM for the digital group. So for example here, clear screen, clear, you're actually calling a routine located at address E6, which is the clear screen routine in that ROM. We have a simple print function that will go ahead and it calls the print character routine in that ROM as well. And you can also read a character from the keyboard, which we do by inputting port 0 on the Z80. We have several blocking version. We can read a string, print a character, delay function. So this is all stuff put together. It's just very basic stuff to make a C program that compiles on a digital group. And then in this case, I'm just drawing some stars on the screen. Or actually, this is the here. Let's do this. This is the easier, simpler version of the program here. Just going to do a simple loop, and we're going to print hello 10 times. So we'll see how that works. In addition to the C program here, it's kind of a assembler wrapper that goes around it, which I'm only now sort of remembering how I set this up 10 years ago. But here, this part is set up as the header for the digital group program. You need this 5353 in the beginning, that octal address. And then these bytes here, you have to actually replace these bytes with the length of the compiled program. So when you compile it and you get object code out, you have to replace these bytes with the size of that program. That tells, that sets like a jump vector, so it knows where to jump to run the code. And here you can see this is actually, yeah, we're including the C program as an include, and then that triggers SDCC to go ahead and compile it. So this whole thing was set up a long time ago, so I don't fully remember how everything works, but it does actually build. So we can actually build this program, compile it, and go all the way down to converting to a WAV file that we can load straight onto the digital group. So let's give that a shot. Okay, we've got the WAV file. Now we'll start up the digital group and load it in. Here we go. Oh, I have to plug it in. That would help. All right, here we go now. There you can see we've got our 1, 2, 3, 4, 5, 9, 10. Yeah, we have 10 hellos on the screen. So it worked, and we've successfully made a new piece of software for the digital group in 2022. So let's try something a little bit more advanced. Let's see if we can make something animated. Let's make something move around the screen a little bit. So this is the next program we're going to try. This is something very simple. So first it's a 64 column display, so I'll just go loop through here and draw the right number of spaces, and then draw an asterisk and insert a delay. So the asterisk should just move from left to right. Then once it's done with that, then we'll just do another loop and we'll move back to the left. So it should just be bouncing back and forth. So no idea if this is going to look decent, but let's give that a try. we go. Alright, look at that. We have an animation. I think that's about the end for part 2 of DG April, where we looked at some of the software options for the digital group and different storage devices, as well as a digital group emulator and building some new software for the digital group. Like I said, I have access to some of the audio format software in the digital group, including a few games and some utilities, but software for this computer is pretty hard to find. So if you have any information about where we can get some of the disk software or how we can get that archived, please feel free to leave a note in the comments. We'd be very interested in hearing about that. There is a fellow named Brian who runs a site called bytecollector.com who has a good collection of digital group software on there. That's pretty much the best and only resource out there with some of that software archived, but always looking for more. And I hope you enjoyed watching. If you liked the video, please feel free to like the video or subscribe to the channel, and hope to see you next time.